The clouds. All right, so welcome everyone. Today it's my pleasure to introduce Peter Humphries, who will be talking about restricted arithmetic quantum unique ergodicity.
All right, thank you for the introduction, and thank you for the invitation to speak. So what we're talking about today is work in progress, so hopefully it'll be done sometime, well, probably not this year, but hopefully sometime early next year. So the general setup, and I'll quickly specialize to kind of a more number theoretic setup. The general setup is something complete from analysis where that you start with a manifold. Usually you want your manifold to be compact. I write here n-dimensional, but in practice you can think of this as a surface, like a two-dimensional manifold. And as your first intuition, you should take something like the n sphere. So the sphere in Rn plus 1, this is the n-dimensional sphere. And what we want to study are certain functions on these manifolds, which are Laplacian eigenfunctions. So if you have a Riemannian manifold, this comes with a Riemannian metric, G, and then from this you can define certain differential operators. One of these is Laplacian, which is this operator here. It's a second order linear differential operator, partial differential operator, and we're looking at eigenfunctions of this differential operator. So functions on our manifold, such that when you act on them by Laplacian, you get back to your original function times a scalar, which is the eigenvalue. And if you put a little minus sign at the front of this Laplacian, then you end up with ensuring that the eigenvalue is always non-negative. I'm also going to ask that their eigenfunctions be L2 normalized. So you can show if you have the Laplacian eigenfunction, it has to be square integral, and you can normalize it so that's L2 norm is 1. Here, there's like a natural measure on your manifold, the Riemannian measure. So intuitively, you can just think of what happens on Rn, which is just the Laplacian is just the sum of the second order partial derivatives, and you put a minus sign out the front to make sure that the eigenvalues here are non-negative. Okay, so this is the setup in general, looking at Laplacian eigenfunctions on a manifold. But we are number theorists, and we want there to be some additional number theoretic structure. And so the first additional structure you can put in is by asking your manifold to be a locally symmetric space. So the way you do this is you start with a Lie group G. You mod out by the right by a maximal compact subgroup K of G, and you mod out on the left by a lattice gamma of G. And you can do this for basically arbitrary Lie groups and get something interesting. But if you want to keep yourself pretty grounded, you take kind of the first interesting kind of non-abelian example, which is when G is the matrix group SL2R, and its maximal compact subgroup is SO2, and okay, the most interesting lattice in there is SL2Z. So then when you mod out G by K in this case, so SL2R mod SO2, you can show this is naturally identified with the upper half plane, H. And then if you mod out on the left by SL2Z, you end up with a modular surface. And we all know that the fundamental domain for this you can just take to be a set of points x plus iy, where x is between minus a half and a half, and you're outside the unit circle in the upper half plane. And in this case, you get some additional structure, which is that when you study Laplacian eigenfunctions, you don't just get arbitrary functions, you get automorphic forms. And that's coming from the fact that you have this modding out on the left by gamma. So the fact that you're asking for your functions to live in the upper half plane, but also be like gamma invariant and a Laplacian eigenfunction means this is the same thing as asking that you're studying automorphic forms. Okay, so let me say a little bit more about Laplacian eigenfunctions on modular surface. So first of all, the upper half plane is negatively curved. It has constant negative curvature 1. So when we're looking at these Riemannian manifolds, in this case, manifold is negatively curved. Next, there's a natural metric, which I couldn't bother to write down, but there is a metric on the upper half plane, and from this you get a resulting metric on the modular surface. So you have like a natural Riemannian metric, gives you a distance function. And from this distance function, you can work out the Laplacian. Okay, this is like a boring exercise in Riemannian geometry, but you can kind of work this out explicitly. And you find that in this case, the Laplacian is not quite the same as the Euclidean Laplacian. You also have to multiply through by y squared. Okay, so you can at least explicitly write down what this differential operator is. You also have a natural volume measure. Okay, often in Riemannian geometry, you want to kind of normalize your volume measure here. I'll leave this unnormalized. So the volume measure is d mu of z, which is dx dy over y squared. And this gives the modular surface volume pi over 3. Sometimes you want to renormalize this and put this here, but it doesn't make any difference. Okay, so this volume measure ensures that actually this this volume measure is SL2R invariant. So this is a nice kind of measure with respect to the group structure underlying it. Okay, so let's look at the Laplacian eigenfunctions. Well, obviously you can just take a constant function. That's not very exciting. Constant function is Laplacian eigenfunction with Laplacian eigenvalue 0. The non-constant Laplacian eigenfunctions are mass forms. So these are a special type of automorphic form. So these are basically functions in the upper half plane that are left invariant by SL2Z, and then an eigenfunction of this second order partial differential operator with positive eigenvalue. And we usually write the eigenvalue as a quarter plus TG squared. The Selva eigenvalue conjecture tells you that TG is real, and this is at least known for SL2Z. Okay, I'm kind of super into the rug that we also have a continuous spectrum, so there are also Eisenstein series. These are not square integrable. Usually, as an analyst, we'll talk about Laplacian eigenfunctions. They'll always assume that everything is square integrable. Here, things are a little bit complicated because the modular surface is non-compact, so there is a continuous spectrum rather than just a discrete spectrum, and these corresponding Laplacian eigenfunctions are not square integrable. But I won't really talk much about Eisenstein series. Okay, at least if you look at the space spanned by mass forms, well, yeah, this will give you a nice L2 space. It's kind of a subspace of L2 of H mod gamma. And there's a nice orthonormal basis of this that is they're not just mass forms, but also Hecke mass class forms. So everything is an eigenfunction of every Hecke operator. In practice, I will be using the fact that you have Hecke operators, but I kind of will be sweeping all this under the rug. It is important. I'm studying things that are the eigenfunctions of Hecke operators, but only in the sense that I want everything to have all these L functions to have all their products. All right, so more on that later. All right, so what do these look like? Well, here's the kind of graph that I always include in all of my talks that I stole somewhere off the internet ages ago. I can't remember where. This is a graph of basically the density plots of 6 different mass forms of reasonably large eigenvalue. And this just shows basically this region here is the fundamental domain for the modular surface. And this picture here is a density plot of how large the absolute value of a mass form actually is. So you can see, like there are these kind of weird symmetries, and the dark bits are where it's very large. There are some bits where it's very large and some bits where it's very small. And it seems to be kind of like scrunched up more down here than up here. But in practice, that's just because the hyperbolic metric kind of squeezes different distances differently down here versus up here. And you can see all these pictures look slightly different, but they all have kind of like similar kind of random, they look a bit like a random wave in some sense. Okay, so these are the objects that I'll be studying this talk, and I'll be talking about kind of properties when you look at these kinds of pictures, some properties that you might expect based on these pictures. So the first property is a conjecture due to Rudnick and Sarnak, and this conjecture is posed quite generally. This conjecture is something that's stated for arbitrarily compact Riemannian manifolds that are, say, negatively curved. And the idea is the following: you take your Laplacian eigenfunction G, and you take its absolute value squared. Remember, we're L2 normalizing this, and then you integrate this against a test function f, and you do this for each G. Now, for Laplacian eigenfunctions, there are infinitely many of them. There's an orthonormal basis of them, and their eigenvalues go off to infinity. So you say, like, take any sequence of Laplacian eigenvalues of increasing eigenvalue and look at this integral of G squared against f on your manifold. And the conjecture is that as the eigenvalue tends to infinity, this should just converge to the integral of f. And if this should be true for every continuous bounded function f on your manifold. Equivalently, you can replace f with the indicated function of a sufficiently nice set. So a continuity set, so something a set whose boundary has measure 0. If you do this, then this conjecture states that the integral of G squared over a set B should converge to the volume of B. And in shortly, what you should think of this as saying is that the L2 mass of your Laplacian eigenvalue equidistributes. It spreads out randomly on your manifold as the eigenvalue increases. So your eigenvalue is just as likely to be large in one region as isn't to be any other region. It doesn't kind of concentrate in one area. In particular, it kind of evenly spreads out with respect to the volume measure on your manifold. Okay, so this is a conjecture of Rudnick and Sarnak from, I think, 1994. They pose it for compact Riemannian manifolds with negative curvature. Of course, the modular surface is non-compact, so you have to modify this conjecture slightly, but it still should be true in that case. Right. In general, this is just a conjecture from analysis. This has nothing to do with number theory. This should be true for kind of any negatively curved manifold. And in this kind of general setting, it seems very, very hard to prove definitive results. So we can show at least that the condition that you have negative curvature seems to be essential. There's a breakthrough result of Andrew Hassel from about 15 years ago who showed that if you don't have negative curvature, then this conjecture, this quantum ergodicity conjecture fails. So you can have scarring of mass with all concentrates in one area rather than spreading out randomly. And even this is true even if your manifold has like ergodic geodesic flow, you genuinely need negative curvature. Much earlier than this, it was known, going back essentially to work of Schneermann in the 1970s, that this quantum ergodicity conjecture is true from almost all eigenfunctions. Basically, you can delete a kind of a bad subsequence of Laplacian eigenfunctions and ask that this same statement hold, but now only taking a limit along this subsequence of eigenfunctions once you've deleted the bad guys. And then these results hold, and in fact, they hold in some greater generality. And the subsequence they delete has kind of density 0. So it seems to be almost true in that sense, but there could be some bad eigenfunctions. You just kind of eliminate this possibility a priori. What else is known? Well, if you take any kind of subsequence and you ask, does this converge to something? So this is saying that if you take any subsequence of Laplacian eigenfunctions, you should have this convergence here. Well, you might, instead of converging in this sense, you might converge to this integral against some other measure. You can ask what the other measure might be. And then Terman showed in breakthrough work about 12 years ago that, well, this might be the case, but whatever other measure you converge to, it has to have positive entropy. There's a notion of positive entropy of a measure that shows you have to like a certain sufficiently large amount of randomness. In particular, you can't completely concentrate on something like a geodesic. And more recently, about 6 years ago, Doutlop and Jin showed that, again, if you have this kind of subsequence converging to some measure, that measure has to give positive measure to any non-empty opening set. So these are kind of partial progress results towards QUE, but they certainly fall well shy of actually proving the conjecture. Okay, so this is just for general compact Riemannian manifolds with negative curvature. It says nothing arithmetic, no number theory going on here. If you do impose some number theory, then you actually can prove something. So this was breakthrough work of Elon Lindenstrauss, published in 2006, who showed that QUE holds on the modular surface. Okay, this is not quite true. He needed to assume, first of all, that instead of just assuming that your Laplacian eigenfunctions, so just assuming your mass forms, he also needed to make sure that your Laplacian eigenfunctions are additionally eigenfunctions of Heck operators. So he wanted the Heck mass cusp forms here. And then he showed that, again, you have this QUE result here on the modular surface. He didn't quite show this. He showed this if you had H mod gamma, where gamma is now a particular subgroup for which this quotient is compact. In a non-compact case, he couldn't eliminate the possibility that there was escape of mass. But then Sander-Arajan proved 4 years later that there is no escape of mass. So this kind of completed the proof of quantum ergodicity on the modular surface. Much earlier, there was work of Luo and Sarnak, and this is kind of more relevant to the talk in terms of the methods involved, that showed, well, if you look at Eisenstein series, so if you look at Laplacian eigenfunctions in the continuous spectrum, well, these are not square integrable, so you can't integrate necessarily against a continuous bounded function because these blow up at the cusp. But if you eliminate that possibility by instead integrating against continuous compactly supported functions, so you kind of don't have to worry about the blow up at the cusp, then you do get QUE, except you have to kind of mitigate by saying, well, actually, these grow a little bit. They grow like a log of the eigenvalue, so you have to divide through by log of the eigenvalue. And once you do this, you get this equidistribution result for Eisenstein series on the modular surface. I've stated these both here for either continuous bounded functions f or for continuous compactly supported functions f. But again, you can take indicator functions of nice sets, and you get this kind of equivalent version where in this first version of Lindenstrauss, you integrate the absolute value squared of a Heck mass cusp form over some nice set B, and this should converge to the volume of B divided through by the volume of the manifold, which is pi over 3. And so for Eisenstein series, you integrate your Eisenstein series squared over a nice compact set B. You divide through by log of the eigenvalue, otherwise this kind of blows up. And then again, you get this equidistribution result. So this is just saying that Heck mass forms and Eisenstein theories spread out randomly on the modular surface, and there's kind of an exact way of quantifying what you mean by that. So again, this is just basically saying that these Eisenstein series and these Heck-and-Mass cusp forms look random. They behave like random functions. And this is not too surprising when you look at these earlier graphs that I showed of these functions. They do kind of look pretty random. So it's not too surprising that they don't concentrate completely in one area. Okay, so I should mention that before Lindenstrauss proved his result, there was an earlier conjecture of Luan-Sarnak, which was kind of a stronger version of QUE, which is quantifying exactly how you get equidistribution in this setting. So instead of just asking that the limit as the eigenvalue goes to infinity of this thing should converge to this, you say, well, take this, subtract off the difference, and ask how big this is in terms of the eigenvalue or the spectral parameter. So in particular, say you take like particularly nice sets, like you take your set B to be a ball of radius r centered at the point W, you integrate your mass form squared over this ball, and you subtract off what you expect, which is the volume of the ball divided by the volume of the manifold. Well, QE tells you that this difference here goes to 0, and Luan-Sarnak conjectured an effective version of this, which gave you an explicit rate of conversion. It says this difference decays like the spectral parameter to the minus a half, so the eigenvalue to minus a quarter. And this decay is kind of uniform in terms of all nice sets, or over all balls in your modular surface, you have this uniform decay. And I should mention Lindenstrauss's proof was by ergodic methods. It was soft analysis, not hard analysis, so it did not give any effective rate of decay. It gave no rate of equidistribution. All he shows is that this expression here is little o of 1. He does not give any rate whatsoever. So this is something quite a bit stronger than Lindenstrauss's result. Of course, Lindenstrauss's result was a huge breakthrough, but it just is not effective. It doesn't give you any kind of rate of equidistribution. Okay, so this is what Luan-Sarnak conjectured in 1995, and okay, they stated, but it was only proved about 5 years ago. Actually, this is essentially sharp. You can't beat TG to the minus a half. So if true, this is the optimal rate of equidistribution. This would be optimal. And it was proved 7 years ago by Matt Young that this is actually true. This conjecture is true, at least if you believe the generalized limit of hypothesis. This follows from earlier work with Watson. Young actually wasn't aware that he proved this conjecture. He was proving something else. And then there's recent work at myself and Jesse Thorne, and we're like, hey, is this conjecture known of Luan-Sarnak? And we realized it literally follows immediately from Young's result. He just does not mention that this is true, but it's known. All right, so I'll first kind of sketch why this is true, and then I'll start getting on to kind of the applications I've applied. All right, so why is this true?
Can I just ask you from, you say it's essentially optimal. This is just from looking at like Veil's law kind of argument, or?
So you average this over G, and then there's like an averaging argument to show that you actually have an asymptotic for an average, and then you drop all but one term, and you kind of get a lower bound of this. So it's related to something called the quantum variance. And if you pay attention to the quantum variance and you get an asymptotic, you drop all but one term, you show that like there must be terms which are at least as large as this.
Okay, thank you.
Okay, so the way you prove this result is basically by spectral expansion. So this is kind of a classical result. It's really something about Hilbert spaces, which is you take some elements of this L2 space, H1 gamma, and you ask, how can you write this in terms of automorphic forms? We can write this as a linear combination of the constant function, sufficiently normalized. So f naught here is just 1 over the square of the volume, plus a sum over all Heck-and-Mass cusp forms. So you're projecting the Heck-and-Mass cusp form and multiply by it, and an integral over the projection onto Eisenstein series. And here, this is the usual Peterson inner product. So this is just writing any function in terms of automorphic forms. It's a discrete sum plus a continuous integral. And now we're going to apply this when we take phi to be the indicator function of a ball, say. So if we do that, well then, and then we kind of integrate it over against, you multiply by g squared, you integrate over all of the manifold. Well, phi times g squared integrated over your manifold gives you this. The constant term in your spectral expansion gives you this, which is kind of the main term you expect. And then you get the remaining stuff, which is the sum over the discrete spectrum consisting of mass forms, and the integral over the continuous spectrum consisting of Eisenstein series. And so these expressions on the right-hand side, we want to show a small. We want to show this right-hand side decays like TG to the minus a half. Well, there are good kind of average bounds for these expressions here, the integral of f against this indicator function, the integral of isosine series against this indicator function. This is kind of related to the local Weyl law. It's related to the Solberg-Harashana transform. This is all completely explicit. You can all write this down exactly to kind of get a good rate of decay of this expression here. The hard bit is understanding the other terms in this spectral expansion. So you have these guys here, which we understand pretty well on average. Then you also have the integral of your mass form g squared against another automorphic form f, or integral of your mass form g squared against an isosine series E. Now, those of you well versed in the Rankin-Selberg method might understand that you can understand this pretty well by the Rankin-Selberg method using unfolding. This is less clear, this integral of g squared against f. So this is a trivial product. It's an integral of three automorphic forms of the modular surface. And what we do is we relate this to L functions, and then you have to bound these L functions. So this is a famous result of Watson and then kind of extended by Chino. What they show is that the absolute value squared of this integral of three automorphic forms, well, this absolute value squared of this integral is exactly equal to a product of L functions. This L functions involves completed L functions, so it doesn't just include the usual L functions, the usual L product, but also the Archimedean part, the gamma factors that complete your L functions. So these are gamma functions that involve the various spectral eigenvalues, the spectral parameters, things like that of the automorphic forms. So this you can write it explicitly. There is an exact identity. I mean, I've written approximately here, but actually there is an exact equality of this left-hand side with some L functions. And then what I've done here is I've separated out the gamma functions that appear on the right-hand side because they're gamma functions that are complete cell functions. And I've used Stirling's formula to work out how these gamma functions behave. So you have these just normal L functions here, and then you have some gamma functions that behave like this. You have this kind of weird kind of polynomial decay that you can explicitly write down, that I'm not going to get into too much detail. Plus, you eventually have exponential decay once the spectral parameter of TF is larger than twice the spectral parameter of TG. So what this tells you is that this trivial product here looks like some L functions times some polynomial decay, and then there's some exponential decay that eventually kicks in once the spectral parameter of TF is sufficiently large. Right, so you have these L functions here, and I won't get into these too much, but the key thing here is that these L functions are kind of complicated L functions. They're like weird GL3 cross GL2 Rankin-Selberg L functions involving G and F, and they're either evaluated at the central point and a half or at the edge of the critical strip 1. And what we want to understand is that if you go back a slide, remember we're trying to bound this right-hand side so that it's small. And we know how to bound this, but we want to bound this trivial product here. So we want to understand how to bound this thing here. Now, in general, this is hard. This is something known as the subconvexity problem to try and bound these. But if you believe the Riemann hypothesis, or something slightly weak, if you believe the generalized Lindelof hypothesis, then these functions here grow very slowly. They grow no faster than any power of any small power of the spectral parameter of f times the spectral parameter of g. In general, we can't prove anything this strong, and this is kind of why quantum ergodicity is hard. But we believe, at least, that these things grow pretty slowly. The guys in the bottom are easy to control. We have kind of good bounds for these things on the denominator. There's the guys on the top at the central point and a half that are very difficult. Okay, so if you now plug in these bounds and you kind of believe the Lindelof hypothesis, so you believe this is pretty small, and you have exponential decay after a certain point, so a lot of these terms are very, very small. You plug all this back in this expression, you just bound term by term, you use the Weyl law, you can show that this decays like TF to minus alpha. And this yields effective quantum ergodicity with this optimal error term that is sharp. Okay, so in the rest of the talk, I want to talk about some refinements of quantum ergodicity that I've been working on recently. And these go beyond bounds for the discrepancy that I mentioned earlier. So the first is something that I've previously worked on, which is going to be relevant for this talk, which is a way of refining quantum ergodicity to ask for a particular rate of equidistribution. This is also known as a shrinking target problem. I call it small scale QUB. So this is when you look at the integral of your mass form squared over a ball of radius r, and you shrink the ball, you shrink the radius of the ball as your eigenvalue grows. And you ask, well, how fast can I shrink this ball and still get equidistribution, still get the expected amount of mass in this ball? So this is kind of measuring the scale of equidistribution. It's measuring the scale at which your eigenfunctions look random. If you shrink too fast, you kind of go below below the scale at which these guys look random, and you're not going to get distribution. But if you don't shrink too quickly, then you're going to get still going to get distribution. And so there's work of Young under the Lindelof hypothesis that shows you can your radius can shrink like TG minus 1/3. And I showed that if you kind of average over almost every ball, then you get down to the radius being just a little bit larger than 1/TG. And this is kind of optimal. This is essentially sharp. This is like the sharp scale which you can expect for distribution. So what I want to actually focus on this talk is what I call restricted QUE, restricted quantum Ergodicity. And this is a changing of the problem where instead of taking g squared and integrating against the function f of your manifold, you now don't integrate over your whole manifold, but you integrate over a submanifold, like some sort of nice curve, for example. And this is much harder because you're kind of looking at a much sparser behavior of your eigenfunction. You're asking, does my eigenfunction still look random along a curve, or does it concentrate along a curve? These questions, it's much more refined. Certainly Lindenstrass's method doesn't give you anything in this regard. Okay, so what do we know? Well, in the last 10 years, there's been a bit of progress. So at least as for arbitrary compact manifolds, this is work by some analysts, by Toth and Zeldrich, by Datlov and Zworsky, that you can get restricted quantum Ergodicity if you delete a bad sequence of subsequence of eigenfunctions. And if you're restricting to a particularly nice submanifold, like what they call a generic hypersurface, which I won't get into. I'm going to concentrate on in the automorphic setting, where I can explicitly tell you what my SERPs will be. Recently, there's been work of Young, who's proven restricted quantum Ergodicity for Eisenstein series. Eisenstein series is a little bit easier to prove things for. When restricted to a vertical geodesic, so a geodesic on the modular surface that just literally goes straight up. And finally, there's been recent work of Yuki Hu, who proved a kind of analog of restricted quantum Ergodicity in the level aspect, in the depth aspect for certain cusp forms. I won't get into much of this. In this sense, the problem is in some sense much easier in the depth aspect, but this is quite a different version of this problem.
Sorry, Peter, can I just ask you, for Young, is it important that it's specifically vertical, or that's
yes,
transversal to the Horst cycle flow in some way, or
he uses the Fourier-Whittaker expansion in a particular way, and this only behaves nicely along vertical geodesics. Yeah, so you genuinely need, it isn't, I will talk about other curves in the end, and you can generalize this in many ways. And so the version I'm going to talk about is the work in progress that I'm proving. Okay, I say, well, there's no way this is going to be done in 2023, but hopefully be done somewhere soon in 2024. So what I prove is the following. We'll work on the modular surface, so H1 gamma. We're going to take our submanifold to be a closed geodesic, and I'll talk a little bit more about this in a second. We need to assume the generalized Lindelof hypothesis, so we need to really assume something quite strong about the size of Bell functions. And then for sequences of Hecker-Mass cusp forms with increasing eigenvalue, I show that we have restricted quantum Ergodicity. So what this means is that for all continuous functions psi on our closed geodesic, if I take my Hecker-Mass form G on the modular surface, I restrict it to closed geodesic, I square it, and I integrate it against this test function psi, this converges to the integral of psi as the eigenvalue tends to infinity. What this is saying is that the L2 mass of your Laplacian eigenfunction, your Hecker-Mass cusp form, spreads out randomly on closed geodesics as the eigenvalue tends to infinity. So these functions look random on a closed geodesic. Okay, I need to assume the generalized Lindelof hypothesis here. So I need to assume Riemann. This is quite a strong assumption. But in some sense, this is a much harder question than what Lindenstrass proved. So it's not too surprising that it seems harder to do this condition. Next, the proof is effective. So just like Young's effective proof of quantum Ergodicity with like an explicit rate of decay for the discrepancy, I can give an explicit rate of decay for the discrepancy. So if instead of taking psi to be like a continuous function, I can take it to be like the indicator function of an interval. And then I show that, well, if I look at, this should converge to this, and I subtract out the difference, and I ask how big this is, it decays polynomially with the spectral parameter of G. The optimal bound is, again, probably TG to minus a half. My method doesn't give this. I think, hopefully I can get down to like TG to minus a quarter, but it's certainly not down to all the way down. Okay, so this is a result. This is what I call restricted arithmetic quantum unique ergodicity. And as I said, it's showing that the L2 mass of Hecker-Mask class forms randomly spread out along closed geodesics. Okay, so let me say a little bit about the method. The proof does not use ergodic theory. This is like an analytic proof, a harmonic analysis proof. It's really kind of relating this to L functions. It's relating this to period integrals of automorphic forms. There's no ergodic theory at all that's used in the proof. I do need to assume that my Laplacian eigenfunctions are Hecker eigenfunctions. I need them to be eigenfunctions of every Hecker operator. And the reason for that is I need these guys to have nice L functions. And if you don't assume your mass forms are eigenvectors of all the Hecker operators, and this is the case. So you need this Hecker assumption. I assume the generalized Lindorff hypothesis, but this is kind of overkill. I could get by with something slightly weaker, but what I need basically are good bounds for certain L functions. And so what I do is I just assume I have good individual bounds, but if I knew good average bounds for them, that'll be fine. But these average bounds would need to be quite strong. They need to imply something called hybrid subconvexity, which is a very hard problem in the analytic theory of automorphic forms. And it's certainly currently out of reach. The kind of bounds that I need do not seem to be able to be proved unconditionally at this kind of time. The method works not just for the modular surface, but for more general things like H mod gamma naught Q. It also works for when you mod out H by some compact, by some congruent subgroup, such that the quotient is compact. So things coming from like, quaternion division algebras. I'll say a little bit at the end how the method also works when you're looking at vertical geodesics. So instead of taking a closed geodesic, you can look at vertical geodesics from a rational point on the real line to the cusp at infinity. And this is a particular case of conjecture of Matt Young from 5 years ago. And finally, you can ask about other curves. And here, I haven't worked in this yet, but there's potential for this to work. The method may also work for something like a horocycle in the upper half plane, so you can kind of restrict your mass form to a horocycle. Also for certain geodesic circles. So you take a point in the upper plane and you take a hyperbolic circle at that point, and that's what's called a geodesic circle. And if the center of that circle is what's called a Heegner point or a CM point, then this method may be able to say something. I'm not sure yet. Okay, so by closed geodesic, this is what I mean. I mean something like this, the modular surface. So in general, geodesics on the upper half plane are either vertical lines or semicircles. When you project them on the modular surface, well, in general, they're just going to kind of spread out randomly. They're going to cover the whole thing because they're going to have infinite length. But closed geodesics are ones that loop back onto themselves in the modular surface, in which case they only have finite length. So this is one example that I stole somewhere off the internet from a student at ETH, I think. I think it was a student of INC. And so this is a graph of what a closed geodesic on the modular surface looks like. It's something like this. It has finite length. It kind of loops back on itself eventually. There's kind of some key structure going underneath, which is that these are related to real quadratic fields. Okay, so in the last 20 minutes, I'll talk about why the proof works. And the key trick that I rely on is the fact that closed geodesics have a bijective correspondence with narrow ideal classes of real quadratic fields, Q adjoint square root T. And you can think of this as saying that closed geodesics aren't just any nice submanifold, they're actually an arithmetic submanifold. There's like arithmetic structure for these curves. The length of a closed geodesic associated to one of these number fields is twice the log of the fundamental unit of this number field. Okay, so for each discriminant D, there are finitely many such closed geodesics. They're equal to the number is equal to the narrow class number. But then, of course, there are infinitely many real quadratic fields. This gives us infinitely many closed geodesics. These closed geodesics are dense in the modular surface. And in fact, there's a work of Duke that shows that they equidistribute in a certain sense. And one of the important things we're going to use is the fact that, well, topologically, a closed geodesic is just a circle. I mean, sure, it loops back in itself, but in terms of like the topology of this thing, this is just a circle, with some extra complications. And this will be good because we want to actually do some Fourier analysis on this, and Fourier analysis on circles is really easy. This is just Fourier series. For simplicity, I'm just going to assume that, well, closed geodesics come in packets. The number of closed geodesics associated to a given discriminant is equal to the narrow class number. For simplicity, I'll assume that the narrow class number is 1. The proof works regardless of whether this is true or not. That's easier for the proof. Okay, so let me first reduce the problem to an easier problem. So we want to show equidistribution. I want to show that the integral of g squared against the test function psi over my geodesic C converges to this thing here, the integral of psi. I need to prove this for every nice test function psi, but by a density argument, I can do this just for a nice subfamily of test functions psi. And those test functions are basically just Fourier modes. There's like either 2 pi I and theta. Once I make a particular change of variables, I can parameterize my geodesic by theta, where theta runs between 0 and 1. And then a nice basis is just given by these Fourier modes here. So I just need to prove them for these Fourier modes, and this is literally the Weyl distribution criterion. The nice thing about this is that the right-hand side then is really simple. This right-hand side is either the length of geodesic divided by the length of the manifold if n is 0, and otherwise you're integrating this from 0 to 1. If n is not equal to 0, then this just vanishes. So otherwise this is 0. This is kind of just when I'm looking for equidistribution. If I want kind of an effective version, then I need actually I need some more control. I need to show like the rate of decay of this. Okay, so I'm going to talk about 2 different ideas of how you go about proving this. Both ideas do not work for kind of tragic reasons, but then what's interesting is that you can kind of modify both ideas and combine them in a certain way to get them to work. So it's interesting that neither idea actually works on their own, and this was more or less known to experts. But when you modify one idea and then kind of go back to the second idea, combined they work. So let's talk about the first idea. The first idea is to say, well, I'm integrating g squared against psi m, and I know how to spectrally expand g squared on the whole modular surface. It's equal to, its projection onto the constant function, plus its projection onto, the sum over Hecker-Mass transforms, plus its projection onto the continuous integral over Eisenstein series. So let me just insert this spectral expansion and then kind of integrate term by term. And you can do that. So if I write g squared, it's a constant function, I get this main term here, plus then the projection onto the cusp form spectrum, the discrete spectrum, I get this expression here, and then there's also an Eisenstein term here. And this is nice because it at least gives you the main term. The constant function, the spectral expansion, will give me the expected main term. And I have this, cusp form contribution, this Eisenstein contribution, and I just want to show that these are small. That's kind of the goal. And now I use 2 things. I use 2 things to try and show these are small. The first is that I already know what this trivial product is here. This trivial product here is related to L functions. And so if I believe the generalized Lindelof hypothesis, I know how to bound these individually quite well. So I can relate these to L functions as good because, at least in analytical theory of automorphic forms, we understand L functions pretty well. The other thing is that I use the fact that C here is a closed geodesic. And that tells me that this integral here of my Hecker-Mass cusp form F against this character e to 2 pi I m theta, this expression here is actually really nice. And this is why I'm assuming that I'm working over closed geodesics. This expression here is related to L functions as well by Weyl-Bourget's form. Okay, so let me talk about this in the next slide. Weyl-Bourget's form tells me that the absolute valued squared of this integral is also related to L functions. It's related to a certain GL2 cross GL2 Rankin-Selberg L function times some junk that is related to gamma functions. So really, this is exactly equal to some completed L functions. And these completed L functions include these L functions here times some gamma functions, and these gamma functions I can estimate using Stirling's formula. They look like this. And just like with the Watson-Nicci trivial product formula, there's some polynomial decay in various ranges, and then you have this factor here that eventually kicks in where you have exponential decay. And the exponential decay depends on whether this parameter, how large this parameter m is compared to the spectral parameter of Tf. So at a certain point, you have exponential decay. All right, so it might seem surprising that you have these L functions here. What's going on here is that well, this function psi m here is actually related to a Hecker-Grossen character of my real quadratic field. And you can use something called automorphic induction to relate that Hecker-Grossen character to a dihedral mass form or a CM mass form. And then once you have that, you can relate this integral here to an L function involving that CM mass form, that dihedral mass form. Okay, so the takeaway here is that this integral of your mass form against this character here, at least when you take the absolute value squared, you get L functions. If you believe the Lindelof hypothesis, these L functions are not very big. And then you also have some kind of stuff coming from gamma functions, and you can control this explicitly. You know exactly how big these are. So this is more or less harmless, and then you have some decay here. So if you go back to this expression here, you have this expansion, you have your desired main term, and you have these remaining terms here, and this term is related to L functions, and this term is related to L functions, and you're summing over all F. Eventually, there's exponential decay after a certain point, so this sum, even though it's over an infinite sum, really can kind of be truncated. And so now you're just like summing these L functions, and you can kind of try to do that, using the Weyl law and using bounds for these L functions. All right, so we're trying to show that this expression here goes to 0 as the eigenvalue goes to infinity. That would prove effective QUE, that would prove restricted QUE in this case. So all we do is we just take absolute values of everything. We apply the triangle equality. We input the Watson-Chino and Vals-Paget formulas to relate this to L functions. We bound the L functions by the Lindelof hypothesis. And then we have these gamma functions, and we bound those using Stirling's formula. And then we just sum everything. And you kind of break up the sum using the Weyl law, and you just estimate everything. And what you get is that the sum basically looks like this thing here. And then when you use the Weyl law, you get that this looks like TG to the half. And that's really bad, because we wanted to show that this goes to 0 as TG goes to infinity. But in fact, the upper bound we got, grew with TG. Okay, so this is bad. And the reason why it's bad is twofold. Well, the reason why we're not getting decay is that the first thing is that we're taking absolute values of everything. That's kind of losing all the oscillation of these terms here. So that's a very lossy step. The second issue is that this sum, well, even though these terms eventually have exponential decay, the exponential decay doesn't kick in until TF is bigger than 2TG. So eventually these things decay exponentially, but for a long time they only kind of decay polynomially, and that polynomial decay is okay, but it's such a long sum that you don't get enough cancellation. So if this sum were much shorter, if this sum were like, instead of going all the way up to 2GD, went to TG to the delta for some small delta, then you'd be fine. So somehow we need to truncate this sum, but it's not clear how you can do that. Okay, so that's the first approach. It does not work. It fails quite badly. You lose by a lot. The second approach is to again use a spectral expansion, but it's a different spectral expansion. So now we use the fact that we're integrating over closed geodesic. Closed geodesic is basically a circle. And we're integrating G times psi m times the conjugate of G. So you group G and psi m together, you group the conjugate of G separately, and you think of this as being like, well, this is like an inner product over this space here, so I should just expand this using Parseval's identity for this L2 space of your closed geodesic. So basically, you insert the Fourier series of these things. So on the one hand, you get G times psi m times psi n. On the other hand, you get the conjugate of G times psi n. And here you sum over all n. So this sum over n is like the Fourier series when you're doing Parseval's identity on the torus. Okay, there's a nice trick, which is that psi m times psi n is just psi m plus n, because e to the 2 pi m theta times e to the 2 pi I m theta is just you sum m and n together. Okay, so this is a different spectral expansion, completely separate to last time. But now it's just a sum over n rather than a sum over Hegemas forms f. So it's expanding over a smaller thing. Instead of, in the previous case, we're expanding G squared over this space, this big space here, and inserting that. Here we're just kind of using Parseval in this much smaller space. And now I can again say, well, these are related to L functions by Vals-Paget's formula. So I know that these integrals over these closed geodesics give me L functions. So we just take absolute values of everything, and then I insert these expressions, I just bound everything, and then I sum over n. Well, there's exponential decay when n is quite large, so basically you can truncate the sum, so the n is basically smaller than TG. And then these things decay polynomials, they decay like this. And I just sum over n, I just estimate this by an integral. And if I do that, I get an upper bound of basically big O of 1. And what I wanted to show is that this is equal to a main term plus little o of 1. So this is less bad than last time. Last time we got the correct main term, but the error term grew like TG to the half rather than decaying. Here, I don't even see a main term, but I'm not growing. I'm just kind of bounded by a constant. So I'm almost correct, but not quite. So this is better, but it's not quite good enough. There's no main term, but this error term, well, it's not growing, but it's not decaying. So it's still kind of lots of. So these are the two approaches that I have. Neither of them work. They're basically spectrally expanding in two different ways. So like using particle identity in two different ways, one for the big space, H1 gamma, one for the small space, the closed geodetic, and then relating everything to period integrals of automorphic forms, and relating these to L functions, and just estimating everything the best I can. But both of these are loops. Okay, so let's look at this expression here. So I have this sum over n, I have these integrals here, and these relate to L functions. I know this sum begins to decay very quickly when n is quite large, and otherwise it looks like this. All right, so if I'm more careful with this approach, I can actually do something quite well. So in the previous slide, I was assuming Lindelof, but even unconditionally, I can do something quite strong, which is I can actually get good upper bounds for the L2 norm of G integrated over this closed geodetic. So this is like understanding an upper bound for how much mass you might get. So there's work of Ali, she was a master's student of Valentin Blomer, who gave an upper bound, well, that if you believe the Marjan conjecture is essentially sharp, okay, it loses by a little bit. And this is basically using this previous approach and then kind of refining in several different ways. And if you're more careful, you can get all the way down to like big O of 1, but you have to assume Lindelof or the ring hypothesis or something like this. What I'm going to show below is actually you can get the correct asymptotic for this, assuming the Lindelof hypothesis. Okay, so we have these two approaches. Neither works. One gives you a main term, but a terrible error term that grows. The other doesn't give you a main term, but the error term is only a little bit too big. So basically, the second approach only barely fails. When we do this particle identity over your closed geodetic, you get this expansion here, and it's only a little bit too big. So what you need to do is extract a main term from this thing and then show that you also have an error term. So the first idea is to look at this spectral expansion and break it up into ranges and just bound various ranges, assuming the Lindelof hypothesis, just taking up to values, inputting Valspier's identity, yada, yada, yada. What you find is that actually, for most n, this is quite small. It's only some n that's small, but not small enough. So if you just take absolute values of everything and bound everything, you find that when n is outside this range here, you actually get a contribution that does decay in with TG. So the remaining range is small. It's a lower one. So basically what you need to do is you need to localize your sum over n to just concentrate on this particular range here, where all the magic happens. Outside this range, everything is small. So this is yes.
Independent of n?
Sorry?
This range is independent of n?
It's not independent of n. Okay, well, in practice, it's independent of n. When I'm proving this result, if I just want to prove a distribution, I can think of m as being fixed. The Weyl distribution theorem just says like integrate against a fixed test function. When I want to do like an effective result, then I want m to vary. So if you think of m as being fixed, then this is true. If you think of m as varying, then it's like almost still true. As long as m doesn't grow too fast with TG, like if m is like smaller than like TG the 1/4, this method still works.
Okay, thanks.
Okay, so anyway, you localize this range here, and that's the range you care about. Everything else is small, you don't care about it, but you can actually prove that it's small. So this is where the magic happens. The next thing is quite complicated, which is to modify your integral of automorphic forms by replacing, well, you have integral of g squared, so g times g conjugate, and you replace g conjugate with something else, a different automorphic form. And this automorphic form closely approximates your original automorphic form g along the closed geodetic, but it's quite different everywhere else. And basically, you should think of this as taking g and taking some crazy infinite linear combination of raised and lowered versions of g. So it's like an infinite linear combination of these guys of arbitrary weights. So now instead of living in the upper half plane, this really lives on SL2R mod gamma. It's no longer weight 0. It's no longer a fixed weight. It's a linear combination of arbitrary weights. And you choose g tilde, this new function in such a way, this crazy linear combination in such a way that in the range of n you care about, the integral of g against psi n over this geodesic very closely is approximated by the integral of g tilde against psi n. So in this particular range, you choose g tilde such that in this particular range, these expressions look the same. And you also choose g tilde to be such that in every other range, this thing here is very, very small. It's exponentially small. Okay, so this is quite complicated. I mean, the way I do this actually is, Delic uses some automorphic representation theory, but the kind of classical way I think about this is just like using raising long operators and taking linear combinations. All right, so the upshot is that I've changed my automorphic form. It's an automorphic form that lives inside the same automorphic representation, but it no longer has a weight 0. It has it's a linear combination of different weights. Okay, so now this is my original problem. Look at the integral g squared against psi m and expand this way. And now I replace g conjugate with g tilde conjugate, and I expand this as well. So my original expansion was this, and my new expansion is this thing here. So all that's changed is that g is being replaced by g tilde. And I chose g tilde in such a way that this thing here looks exactly like this thing here in the range of n that we care about. In the remaining range of n, I chose this is exponentially small, so like this doesn't contribute. So this doesn't closely approximate this when n is outside this range, but I already knew that the sum of these guys outside this range is small, so I don't care that the approximation is good. I only care about the approximation in the important range. So the upshot of this is that I can show my original expression, the integral g squared against psi m, is closely approximated by this new expression, the integral of g against times g tilde times psi m, plus a small error term. And this error term, and I can show decays with TG. So I've literally just kind of changed my automorphic form in such a way to kind of localize to this regime here, and this changes the problem in a small way. All right, so far this might not seem useful. What I've done is like change the problem a little bit, but I still have to actually show that this gives me the correct main term and the error term. But now I go back to the first approach that I initially had. So I take g times g tilde, and I especially expand this over L2 of SL2R mod gamma. So here it's important to notice that this function here is no longer a function on the upper half plane, it's a function on SL2R, because it's like an infinite linear combination of raising and lowering operators. So this is like a more accommodated function, lives in the bigger space, but there's still a nice spectral expansion. And when I spectrally expand, I get a main term, which is a little bit more complicated, plus a sum here over cusp forms, plus an Eisenstein contribution. But it's a little bit more complicated than that. So the spectral expansion doesn't just include Hegemar's cusp forms of weight 0. It also includes things of arbitrary weight, of arbitrary even weight. It also includes things coming from holomorphic cusp forms. It also includes like raised and lowered holomorphic cusp forms and raised and lowered Hegemar's cusp forms, raised and lowered Eisenstein series. So it includes like all even weights and all holomorphic forms of all of those weights. Okay. Now what's nice is you still have a main term here. This main term here looks a little bit different than last time because you have this expression here. But you can show that if I choose g tilde correctly, this basically looks like 1. So this expression here is equal to my main term plus a very small error term. And now what I need to do is show that these remaining terms here are small. And this might seem difficult because, well, last time we failed miserably when we did this. Our spectral expansion was way too long, and we showed this grew like the best I would get was t to the half. This was really bad. And it looks like we've made things worse because now we have an even bigger sum here. It's not just over weight 0 things, it's over arbitrary weights. So this does look like it's making the problem harder. But it turns out it's not. So we do the same strategy as last time. We just take absolute values of everything, and then we relate the integral of this trivial product to some L functions. We relate this integral here over this flow geodesic to L functions. So this is by Watson-Neutrino formula. This is by Walsh-Bourset's formula. These are related to L functions. And they're also related, they also involve weird gamma functions. But the way I modify g tilde actually changes those gamma functions. And because I'm taking an infinite linear combination of these guys, I have like an infinite linear combination of gamma functions, which is something really quite complicated. So what this has the effect is that instead of last time where I had these guys involving gamma functions, I have a much more complicated weighting function than a gamma function. It's much more complicated. So again, this looks like it's made the problem harder, but I can try to understand the size of these gamma functions. So this is like the last key step. I want to show this guy is small, and the way I need to do that is to use the Watson-Neutrino formula and control the size of this weight coming from infinite linear combinations of gamma functions. So I used some complicated work, following work of Paul Nelson on Monahashi's formula. I used some major stationary phase analysis, and you have to estimate a bunch of integrals of things. And this is like the heartbeat of the problem. And the option is eventually, if you're really, really careful and you estimate everything very well, you can show, well, actually, the weights that you get here, these infinite combinations, look pretty similar to last time in a certain range. They behave similarly as the previous gamma functions, at least when TF is pretty small. But now you get exponential decay quicken. You get exponential decay kick in much faster. Previously, exponential decay kicked in way too late at 2 TG. Now you get exponential decay at TG to the delta, or some small delta. So this approach is still quite bad in the sense that you're taking absolute values. So you're kind of forgoing a bunch of cancellation here and the fact that these things may have different signs. But by replacing G with G tilde, you actually manage to shorten the sum over F. You get exponential decay much quicker, and that wins. That is why you're able to show that this is small, because the spectral sum is much smaller. Okay, so in the last 2 minutes, I will mention some interesting generalizations that I have not studied yet, but I think are interesting questions to study, which is, does this method work for curves other than closed geodesics? There are plenty of other interesting curves on the modular surface you could ask to restrict your automorphic form to and ask if you get randomness. And well, you have to look at the method of this proof and ask what works for other curves. So the key idea behind this method was, we had these two different spectral expansions, and at least when you're spectrally expanding over your closed geodesic, you had this nice Fourier series expansion, and then these Fourier series coefficients were related to L functions by Gauss-Braze's formula. And we knew at least what good bounds for these L functions should be. So you need such similar results for other curves. So you might ask, when do we know how to relate integrals of automorphic forms along curves to L functions? And there are three that I know of. The first is when you have a vertical geodesic from a rational point to I infinity. In this case, these integrals are what's called the Heck integral. They give you L functions. The second is when you take a CM point, a Heegner point, and you take a geodesic circle centered that point. And then a different version of Gauss-Braze's formula that doesn't seem to be written up anywhere in the literature, but I'm pretty sure is true, relates this to L functions as well. And the third is slightly different, which is that if you integrate automorphic form along the horocycle, you get Fourier coefficients. Okay, these are not L functions, but at least if you believe the Ramanujan conjecture, these are pretty small. So you similarly kind of expect these are like arithmetic curves, and you similarly expect these integrals to be pretty small. And then you're left with like three problems. The first, if you take a vertical geodesic or a geodesic circle or a horocycle, in each case you have to do the same strategies. You have to somehow modify G to be replaced by some function G tilde, and it's going to be different in each case. And then you need to show that this new function closely approximates G along this curve that you're given. And the final bit is a very, very hard bit, which is so that the spectral expansion, the second spectral expansion, is sufficiently short. So that's the difficulty. So I haven't tried any of these. I think these might be feasible. I don't know if they'll work. I think it's an interesting problem, but it seems very difficult. But these are kind of the state we're in. And if you change the problem very slightly, so instead of doing a vertical geodesic from a rational point, you just do it from an arbitrary point, then the method fails completely. There's no connection to L functions, and I have no idea what to do. And same thing if you do like a geodesic circle, not to the Heegner point, but it's like an arbitrary point. There's probably no relation to L functions, and then I have no strategy whatsoever. All right, I'll stop there.
Thanks a lot, Peter. Other questions from the audience? Let me perhaps beforehand stop the recording.